Yeah, recording has started. Welcome everyone to Quantum Computer Fundamentals. Few things I want to mention specifically because we were on the Santa Clara Computing Meetup group, which we dismantled and we have moved to Silicon Valley Quantum Computing Group. Taposh is here. Hey, welcome Taposh. He's the one, courtesy to him, we were able to move. Taposh, you want to say a word or two? Go ahead.
No, I just want to say thank you, Prakash, for continuing the teaching effort, and I'm very happy to support you in any way or form. I mean, certainly you are doing the heavy lifting here. Yeah,
No
thank
worries, and we appreciate your gesture, and we will continue to work with you on the Silicon Valley Quantum Computing Group, which is growing. If you had known previously you existed, probably I would have not dared to even start a new group, but very good for collaboration. And we will certainly add one more, which we have already said that we will be having one more 6 weeks course, and that is a separate one. This coincides with our Professor Gokhale, who uh, did all his effort from Europe and now from Mumbai. So, to keep his sanity, we want to make sure that it is continued in the same way. And we are going to look forward to IBM QuizKit with the background on the quantum gates, which are critical. With that, I think I will hand over to Gokhale. Gokhale, go ahead. I think we have enough quorum to start. And anyway, we are recording, so we should have the recording put on the YouTube as well as the uh, quantum Silicon Valley Quantum Computing Group, which I have just became aware of, and I will add that. Plus, the week we are canceling the week midweek, that is Wednesday office hours. Instead of that, we'll go into Silicon Valley Quantum Computing's Discord. I'm just attempting, but we will get into that so that everybody who wants to get anything clarified can do that. So we are past 3 minutes. Gokhale, it's time for you to take over. Thank you very much.
Thank you very much and welcome all participants. This is Gokhale Jayanti. I'm signing in from Mumbai, India, and we are on to our session number 9. And incidentally, what we are going to cover today would be a few spillover topics from a previous session. Last session, we did not cover all the quantum gates. Today, we are going to cover the remaining quantum gates, and post that there would be some sort of a uh, demo, or maybe you can call it as a hands-on session, and we will go through using IBM QuizKit. And I'll be spending more time in IBM QuizKit. And pardon me, I'm not turning my video on very specifically because I'm getting too many pop-up messages intimating that bandwidth is not very stable. Mumbai, it's raining very heavily here. I hope the network connectivity holds on. And in case due to any reason, if I drop out, kindly hold on for me. I will try to make some alternate connection and then I'll join in one more time. Okay. So with that said, kindly permit me to share my screen. And I'm sharing my entire screen. Give me a moment, please.
Yeah, go ahead.
Yeah.
I'm not sharing anything, so you should be able to share.
Yeah. I hope you can see my screen, Prakash. Okay.
Yeah, and the
Yeah.
not the slides. Yeah, go ahead.
Yeah.
Yeah,
The slides will be there. Okay. Now you see
yeah,
the
you can
slides, right?
you
Good.
can go to slides.
Yeah.
Yes,
Thank you
yes.
so much. Okay.
Go ahead. You're on slide 3. Timetable. Yeah, we can't hear you. Are you muted?
Hello. Hello.
Yeah, yeah. Now it's fine. Yeah. Now we are able to hear you. But the share is changed.
Yeah,
So
it's
you
not.
share and then go there.
Yeah, I'm sharing. I'm
Share.
sharing. No,
Yeah,
it's
share.
already shared there. I'm just switching out over
Yeah.
here. You can see my screen now.
Yeah. Go to the slide share. Yeah.
Yeah, fine.
Slideshow.
Okay, fine. So typically today we are going to have a quick recap of the gates which we studied last time, and I'm also going to introduce to you three or four more gates: the swap gate, the phase shift gate. We are going to have a quick introduction to the phase shift gate because I propose to go into the depths of the phase shift gate next time when I do the implementation also on the qiskit. And I'm also going to talk about the controlled phase shift gate and the Toffoli gate. So I'll be talking about the behavior of these gates today, but I'll not be showing any of those things in the part of a demo. And I will once again follow the entire demo working on IBM QuizKit. Okay. So a quick introduction. Last time we spoke about the NOT gate. This is a one-bit NOT gate. It should not be called as a one-bit NOT gate, but technically it is a one qubit NOT gate. It operates on the qubits, and the function is pretty very simple. The operator, the U NOT gate operator, works on, let's say, input which is, let's say, ket 0, converts that to ket 1 and vice versa, and you have got an equivalent matrix representation for that in case you wish to implement that using matrix multiplication operations, right? So that is a matrix representation, and remember this is a one qubit NOT gate. So because of that, the complete the operator matrix would be a 2 by 2 matrix in the C2. So this is also called as a NOT gate, and people normally also refer to this gate as an X gate because this matrix represent the sigma X matrix, the Pauli's sigma X matrix, right? So this is your X gate, and the continuing further, I can typically take this gate and operate over any general state, right? And that general state is represented by psi equals to alpha ket 0 plus beta ket 1. And if at all I operate onto that, you will see that the result will be beta ket 0 plus alpha ket 1. So basically it interchanges the coefficients out there, right? And diagrammatically, or the symbolic representation for that happens to be a very simple X there, and then you have got the input state and transforming that to some equivalent output state. The XOR gate is also called as a CNOT gate. It's now once again a NOT gate, but typically we have a mechanism wherein I uh, use some other input mechanism to control the way the gate behaves. So we will also see what exactly is the concept of a controlling mechanism. Now this is a 2 qubit gate, and because it is a 2 qubit gate, it typically operates on a vector in the 4-dimensional C4 space. So obviously the matrix operator representation would be a 4 by 4 representation. We have seen that. So this is the matrix representation. So if at all you take any basis state, like for example ket 10, and ket 10 is represented by this column, and if you perform operations using this XOR, right, and you would typically get the basis state as 1 1. Okay, so how does this basically turn out into a different type of a representation? Now, when you look at this behavior, and here is once again a small example of the same matrix representation of the XOR gate, and I'm using a generalized vector, and this is a 2 qubit generalized vector. So we have the coefficient alpha, beta, gamma, and delta for the 4 different basis states, and I put them into a column format. And if I apply this XOR gate, I would be getting a resultant, and if you see, the resultant will be typically the first two values would be the same values, whereas the last two values are flipped, they are inverted. So what is happening is something like this. Inversion happens whenever one of the bit, right, we call this as the most significant bit, is equal to a 1. So I can now think about the behavior in this manner. That so-called most significant bit, when it is a 1, is now responsible to flip the least significant bit. So it operates as a NOT gate under some conditions. And what is the condition? The most significant bit will have to be equal to a 1. So if you look at the maybe the sort of a state representation in the form of a typical truth table, only when the input A equals to 1, right, whatever is the value at B, that will be flipped. So we now say that input A is the control bit, and the least significant bit, which is flipped, is called the target bit. So the control bit will decide whether the target bit would be flipped or not flipped. Okay, so that is the reason why we say that this is a not operation, but controlled in its behavior by the control bit, right? So once again, the representation from qiskit goes in something like this. The control bit is identified to be on the uh, most significant bit, and then you have got the target bit and the least significant bit. Now the representation once again could be something like this. So this is the typical symbol on the NOT gate, and the dot out there will act as the controlling point. Okay, so that is the behavior for your x0 gate. We have also used the Hadamard gate, and we are going to talk about this Hadamard gate in more detail in the next session, where we actually will discuss the implications of this Hadamard gate. But from the current point of view, the way we are going to use this, the Hadamard gate is a 1-qubit gate, and what it basically does is it takes one basis vector, let's say ket0 or ket1, and then converts this into a superposition of these two basis vectors. So for example, if you are having a ket0, ket0 typically maps onto a superposition of ket0 and ket1 with magnitudes of under root of 1 over under root of 2, whatever. And similarly, if the basis state happens to be a ket1, it combines them into something like ket0 minus ket1 and under root of 1 over root 2, right? So this is basically the way the mapping typically happens. So technically, at this particular point of time, it is good to know the core functioning of Hadamard gate, wherein it takes either ket0 or ket1 and converts that into a superposition of two basic states. Okay, so most often this Hadamard gate is what is used at the input state to pick up your quantum state and convert that into superposition. And the moment you have got that superposition, you now get an entangled type of a state, and that is what is actually operated upon in subsequent stages. Okay. So how do I have the Hadamard gate matrix form representation? It is once again H equals to 1 over root 2 multiplied by this particular matrix representation. And here is a classic example. If I operate the Hadamard matrix on ket0, I get this form, and you can now see the fact that it will be 1 over root 2 and ket0 plus ket1. So this is basically the superposition of the two basis states. And similarly, if I operate H Hadamard gate on ket1, plugging that out over here, you realize the fact that you see the fact that the resultant is 1 over root 2 working on ket0 minus ket1. Just see this particular negative sign. That negative sign is responsible for a phase shift. Okay, so as I told you, we are going to use the Hadamard gate for converting typically any normal inputs into a superposition state. Okay, so we are not going to talk more about this Hadamard gate right now. We will be discussing more about this Hadamard gate and its behavior, because it also concerns with a few bunch of rotation aspects and things like that. So we will talk about that in the subsequent lecture. Okay, what has happened? Yeah, I did not know. What has happened? Prakash, any idea?
I think it's just a glitch. Just try to click on show anyway. Bukleji, hello.
Yeah. Thank you, sir. Thank you so much. Okay, fine. Okay, I told you I'm working on some very poor bandwidth here today. Okay, fine. So we will now talk about the other three gates today, 3 or 4 gates today. So let me introduce to you what is called as a swap gate, and this is a 2 qubit gate. And as the name itself suggests, this is a very simple way by which I can exchange the basis states between maybe any two states. Give me any two states, and I can use this swap primarily to interchange the values. And this is a very common operation that is normally used, but at the same time it's a pretty very tricky operation also. So when you talk about taking one state and transferring down to the some other state, normally in classical computing we try to interchange the values of two variables, and for that reason we normally use a third variable as an intermediate temporary store, and that's how swapping takes place. So in the moment we try to do that, is it that we are going to collapse the gate? No, the answer is no, we are not going to collapse the gate. So internal implementations ensure the fact that the gate states are maintained, or the qubit states are maintained, and we typically ensure the fact that the quantum states of these two variables, or the whatever, they would be interchanged. Okay, so here is a very simple representation for the behavior. If I say that A and B denote maybe the first and the second qubits of any basis state, right? And I can now use this swap function operating on, let us say, state representation AB, and that will result to a state representation which is BA. Okay, so we Prakash, I have some problem. The matrices are not coming up.
Yeah, I think maybe it's the band could be bandwidth, could be just a glitch. Just keep on.
The matrices are not coming here.
Try reload. Try the reload button if you can. This next time it comes up.
Yeah, nothing is coming up there.
Okay. Other slides are okay. This slide maybe there's some formatting issue
No, but
with the geometry.
I wouldn't know. Okay, fine. So once again, like we have been discussing, there is a matrix which is a 4 by 4 matrix acting as an operator, and I can just show you the fact that when it operates on, let's say, ket 01, it will convert that to ket 10. Okay, the slides which are sent to you probably have that. So that's a pretty very simple description out there, right? And there is a circuit representation. The circuit representation is typically in two forms. Let me see if it, yeah, you can see it this way maybe. Okay, so I hope you can see
Yes.
the screen. Yeah, I think
Yes.
this is
Yes.
good.
Very
Yeah,
good.
there is some
It's
issue in
very
the
good.
slideshow. Fine.
Yeah.
So this is my U swap A B, and if at all I just operate on 0 0, it will result to 0 0. Let's say 0 1. Once again, the states will be flipped to 1 0, and 1 0 will be flipped to 0 1, and 1 1 will be retained as it is. So automatically and obviously, what we see is the fact that it is ultimately going to flip the two basis, the two values, or the two state values in the basis states. And I told you this is the matrix representation for the swap, and this is the 2 by 2 sorry 4 by 4 operator, basically because we are working on a 2 qubit gate. And this operator, if at all I try to work it out on ket 01, you can just see that ket 01 column vector is 0010, and if I operate on that, the resultant will be 0100, which is just nothing but ket representation for 01. So 01 10 gets converted to 01. So here I think it should be 10 here. Yeah, fine. Okay. So I can now have a generalized definition even for the behavior of the swap gate. Here I can consider any 2 qubit vector, which is let's say psi. Psi is represented by alpha, beta, gamma, delta over the four basis vectors, and this gives me the column representation alpha, beta, gamma, delta. And if I operate on the 4 by 4 swap matrix, I will be getting alpha, gamma, beta, and delta. Notice the fact that the middle two values would be interchanged. And there are two representations which are pretty very commonly accepted here. So one is this sort of a X or a crossing notation, right? So here you have got the input which is psi getting converted to something like phi, and notice the fact that it is once again flipping of the internal two coefficients. The another popular representation for this is this. So qiskit also gives me this sort of a representation, visual representation. So both of them are two equivalent notations which are popularly used to represent the swap gate. Then you have got a phase shift gate, and let me see if at all I can go to the slideshow. Yeah. Now this phase shift gate, I'm going to spend more time about this phase shift gate a little later on when I do the rotation operations. But the phase shift gate is also called as a P gate. And what does it typically do? It operates on one qubit and tries to change the relative phase shift between the so-called basis vectors. So there are two basis vectors, right? So it will try to change the relative phase between the two basis vectors. And to do that, what it typically does is the matrix representation would be something like this. You have got e to the power of I phi. Now this phi is the phase angle, and e raised to the power of I phi is what is called the phase factor, the factor by which the phase is being altered. So what does it essentially boil down to? If you look at this matrix, if at all you have got a input which is ket 0, the operator does not have any effect on this ket 0. Whereas if the input is ket 1, then it changes that to e raised to the power of I phi ket 1. So notice the fact that this typically accounts to the so-called relative phase change. Okay, so normally we say that this phi is called as a phase value, and the e raised to the power of I phi is the complete phase factor, the factor or the amount by which the phase is affected. So if at all I look at this representation, now notice the fact that the generalized representation once again happens to be like this. I'm talking about the gate U, PS stands for phase shift by an angle pi, if at all I talk about pi, and if that is operating on the plus vector, remember, if at all it's operating on the plus vector, it typically realizes to me the minus vector. So we will see a little more about this, why it is happening when I discuss about the rotation matrix also. Okay, so just keep this a little aside, but that's pretty very important for you also to remember the fact that when we talk about changing the relative phases, especially by values like pi and all that, you have got a different orientation of the entire look and feel of the states of the system. So here is once again the matrix representation, and as I told you, it will affect only ket 1. It will not have any impact on ket 0 because if at all you have got ket 0, this column value would have been 1 0, and with 1 0, the matrix still would be the same. It does not typically change anything. Whereas if at all you have got the state as ket 1, so ket 1 would be represented by the column value 0 1, and if you just multiply that, you get this as 0 e raised to the power of I phi. If you pull out e raised to the power of I phi outside, then this is once again e raised to the power of I phi times ket 1. Okay, so that is why this is also called as a phase shift gate. So how do we represent the phase shift gate? The phase shift gate is typically denoted by this, PS, and you identify what is a phase shift. And when you look at this phase shift gate, more specifically, if the value of phi happens to be pi, okay, then just plug in pi for phi, then this entire matrix gets converted to this, right? And please understand, this is just nothing but your sigma z. So that is the reason why this is also called as a z gate. Remember, we had that the inverter called as the x gate. Similarly, this is called as the z gate. Okay, so for that reason, you also have got this sort of a representation. Okay, and you can also have got extension to this is something where I can have a condition which identifies when the phase shift gate will operate. So that is something called as a conditional phase shift. So let us also look at that part out over here. So that conditional phase shift is also called as a controlled phase shift gate. And this control phase shift gate obviously now will be a 2-qubit gate. One qubit, which is the actual the value, and the second is the result, the let's say the control bit. So once again, you will have the target bit and the control bit. So the control phase shift gate will operate on A, B, and it will produce a relative phase shift, right? Remember, the vector still would be AB, but it will produce a phase shift by a quantum which is equal to I times A dot B. Now, what is this A dot B? This A dot B is the AND operator between A and B, which means what? If A is equal to 0, then obviously notice the fact that there is no effect. If A equals to 1, then only it produces the so-called phase shift out there. Okay, so looking at the overall behavior, so notice the fact that for this guy to work, A and B, both of them have to be equal to 1. Remember, if the value of B is equal to 0, anyway there is no phase shift there that happens. So the phase shift happens only when the value of B equals to 1, like we have seen earlier on. So here, the gate operates only when the B value is equal to 1. If the B value is equal to 0, it does not operate. Similarly here, it has to be B equal to 1. So which also means the fact that A and B, both of them have to be equal to 1. Only then the gate performs a so-called phase shift. So looking at the overall behavior, you have got this controlled phase shift gate, and you identify the phi as the vector, and then phi as the angle. One second. Phi as the angle, and it is operating on the vector 0, 0. It will not have any change, right? See, this will be 0 dot 0, that is AND operation between these two values. There is no change, so you'll get them output as ket 0, 0. Same thing happens even for ket 0, 1 and 1, 0. But when it comes down to both the inputs to be equal to 1, then you have this as E I phi times ket 1, 1. So you now notice the fact that the phase shift is manifested only when both the inputs are 1 and a 1. So that is the reason why this is called a controlled phase shift gate, which is a 2-qubit gate. So once again, the moment it is a 2-qubit gate, the operator has to be in the C4 space, and this will be a 4x4 operator. And here is a small example once again. If it operates on 1, 1, remember 1, 1, if you operate it, the column vector has to be 0, 0, 0, 1, and that operated on this 4x4 matrix will result to you in e raised to the power of I phi multiplied by maybe the ket vector 1, 1 as it is. So this is the what the phase shift that is getting manifested because of this operator. Okay, so that is by controlled phase shift. So this is the general representation for the control phase shift gate. If at all I consider a general 2-qubit vector, and this 2-qubit vector is defined by alpha, beta, gamma, delta as the coefficients for the 4 basis states. And if at all I represent that out over here, alpha, beta, gamma, delta, remember the fact that if the input value is equal to 1, 1, and only then the output will be now converted to e raised to the power of I phi times delta. Okay, so the coefficient would be modified by this particular value e raised to the power of I phi. Okay, then you have got a pretty interesting gate called as a Toffoli gate. Now this is called as a CCNOT gate. So now we have started with 1-qubit gates. Then we came across 2-qubit gates, and now this is a classic example of what is called as a 3-qubit gate. And this is a very interesting gate simply because of the fact that this is also called as a universal gate, right? Remember, in the case of normal classical computations, we have got the NOR gate and the NAND gate also defined as the universal gates. And the reason why they are called as universal gates is the NAND gate can be used to implement any other gate. NOR gate can be used to implement any other gate. Similarly, this Toffoli gate or the CCNOT gate can be used to implement any other gate as well. Right? So that is the reason why this is also called as a universal gate, similar to that of a classical computer. Fine. So let us understand how this CCNOT gate works. And as the name suggests,
Yes,
let's, yeah,
can I ask a quick question? So
yeah, sure,
at a high level, we had in computer science we learned about those gates, right? And then we are using gates here also because
correct.
of. So now we are in the domain of gates that are coming up because of this concept of qubit. So are these gates that now we are doing these advanced gates like Toffoli gate, Hedegaard gate, all that? All that's not
Yeah, yeah, yeah.
relevant to
These are
the
the, yeah,
classical computer science, right? Because that's
yeah, no, no, no,
qubit.
no, not exactly. I don't say not relevant. For example, in classical computer, we do not have a conditional NOT gate. We do not have that. Right
Mhm.
now, if
Yeah.
at all you want to implement this conditional NOT, then you have to implement in a different way. You still can implement using your conventional gates. Here
Okay.
you
Okay.
have them as a basic underlying phenomena in
Mhm.
the context of your classical state representations.
So
Okay. Okay.
Right?
So what?
I will answer this way that we do mix up here, but essentially quantum logics are all reversible, and this particular Toffoli gate is a 3-qubit gate. Normally we do 1 qubit, 2 qubit. This 3-qubit gate has a typical characteristic which can recreate the entire classical circuits because it has a AND and a NOT both available, and if you use a NAND, not an AND, you can build any circuit in classical computer. So that is why Toffoli gets a special recognition that you can implement using quantum gates the computational logics for classical computing
Okay.
in the
Thank you.
semiconductor. That is the reason for this.
All right. All right. Okay. So Gokhleji, all these gates are possible in classical also. Okay. Got it. Fine.
Yeah, you can also implement them in classical, but there is a sort of a workaround. You have to come up with a intermix of the classical computing gates also. Functionally, you
Okay.
can realize this. For example,
Okay.
but phase shift is something which you cannot realize. And phase shift you have got in
Right.
classical gates only the NOT gate. So NOT gate gives you only a 90-degree phase shift.
Right. Right. Okay. Got it.
Uh,
Yep.
So just
That's a
to
good example.
clarify, it is vice versa. You can do classical using quantum using classical high performance computing and GPU with the classical circuits, or you can by simulation, that is quantum simulation. The alternate, if you want to use fully quantum based, then you can use quantum gates
Yeah.
and
But this
combine with
phase shift,
hybrid.
but this phase shift example was a good example of where it's a concept in quantum, but not in. There's no phase shift concept in that. It's only the 90-degree thing. Yeah.
yeah, correct, correct. Yeah.
So yeah, that's true.
Okay. So thank you, Dhaval. Uh, so let me just move down to this Toffoli gate. This Toffoli gate is called as a CC NOT gate. Now we have seen the C NOT gate. What is that C NOT gate? It was a controlled NOT gate. So here we talk about CC NOT gate. That means that controlled NOT gate. The controlled NOT gate itself is further controlled. So which also means the fact that we'll have two controls, right? And both these two controls should be high, should be logically 1, so as to perform the operation of the NOT gate. Very simple. So what we now talk about is, because this is a 3-qubit gate, the matrix representation and its behavior has to be in the C8 space. Right? We now know about that. Earlier on, we had 2-qubit gates which were operating in the C4 space. Now it is a 3-qubit gate. That is the reason why this will operate in the C8 space. So the matrices will be 8 by 8 matrices. Number one. Number two, how does it actually work? The representation is called as a Toffoli T ABC. So ABC now will be the three values to represent any one of the basis states. Remember, A, B, and C can be zeros and ones. So these are the one of the 8 combinations you can get. And technically speaking, moving down to the extreme right, this Toffoli gate representation works something like this. The first value A will be retained as it is, the second value B will be retained as it is, and the third value will be operated upon as follows. Looking at the combination, the AND operation of A and B, if both of them are 1, then only the C value would be complemented. So here A and B together act as the controlling logic. So A and B together have to be 1. Only then the NOT operator would be applied on the third value. Right? So as simple as that. So I can typically say that the NOT operator is applied to the value of the last bit if and only if the first bit and the second bit and of that is a 1. So A dot B has to be equal to 1. Otherwise, it is not applied, and when it is not applied, the value of the C remains unchanged. Right? So here what is happening now, there are two elements which are controlling the outcome. A and B are now the control and C is the target. Okay, so how do we look at that? So here is a small example of the working of the CCNOT gate. I've just given a listing of all the 8 possible states in the C8 space. So here T operating on 0, 0, 0, that's the first state. Because the first two control bits are 0 and 0, there will not be any change. 0, 0 here also it will not be changed. So irrespective of whether the third value is 0 or a 1, it will not flip this, it will be retained as it is. Similarly with 0, 1, there is no change. 1, 0, there is no change. Only when the first two bits are 1 and a 1, the third bit will be complemented. If you see that 1, 1 transform to 1, 1, 1. So 1, 1, 0 finally gets transformed to 1, 1, 1. And 1, 1, 1 transforms to 1, 1, 0. Right? So you have now two control bits and one target bit. Right? So this is something like you're adding an extra control line on top of a normal CNOT gate. So why do we do that? And there's a wonderful reason why we can do that. I'm going to show that to you in the next slide. So here is the matrix representation. Remember, this will be an 8 by 8 matrix. So in case you are planning to work on direct matrices
Can I
to
ask
perform.
you a quick question on the previous slide?
Yes, sir.
Yeah, previous slide. Yeah. So that CNOT gate that you showed us, right there, the concept was the MSB. If the MSB is 1, then the flip happens, right?
Correct.
So here also, in a way, if you think of this 1, 1 as a set
No.
of an MSB, then
No,
a flip is happening.
yeah. 1, 1. That means the first two MSB bits, not one MSB bit. The first two
Yeah,
MSB bits will
exactly.
act as a control. Yeah, you are right.
Yeah, but what I'm saying, but if I imagine, I'm just abstracting a little. So if I imagine, just for fun, I'm saying, if I imagine that the 1, 1 is like a set, it's like a one set, so it's like a 1. So in that case, it's a similar operation as the CNOT gate, right? I
Right,
mean,
you
in
are
that
right.
sense.
You are right. You are right.
I'm just
If
at a
one,
very big picture level. I'm just trying to understand the effect is the
absolutely,
same, right? It
absolutely, you
flips
are right.
when the two MSBs are ones, basically.
Correct. You
I
are
mean,
right. You are right.
MSB and
You
the
are right.
next MSB, that is, I mean.
You are
So,
right.
and I'm sure there's a reason why you need this, so you're showing us that next, but I just
Yeah,
wanted to
yes,
understand
sir.
that.
Yeah, I'm going to show
Okay,
that to you. Yeah,
thanks.
yeah. Okay. Thank you so much.
Thank you. Thank you.
Okay, so this is basically the matrix representation, which will be an 8 by 8 matrix representation. And then this is a small example. I've just taken the state 111 and I'm operating on that. So remember 111 would be a column vector with all zeros, the last bit will be equal to 1, right? And if I operate on that, this resultant will be 1, 1 and a 0. So remember the first two bits are ones, that causes the third bit to be flipped. So when it flips, it just becomes a 0 there. 1 becomes a 0. Okay. So looks very nice, but why the hell am I doing all this? Right? I'm not getting into the fundamental proof of the working for this, but this is there is a nice reason why we can do that, and I will show to you to the fact that this Toffoli CC not gate can now be looked upon as a universal gate. Okay, so once again, continuing in the same format of our discussion, I'm just taking a generalized representation. So I've got the generalized state as psi, and psi is defined by alpha, beta, gamma, delta, epsilon, blah, blah, blah. All these parameters are there. So all of these are one column vector for the different coefficients of the basis states, and then multiplied on the Toffoli will give me this. And just notice the fact that what will happen, uh, uh, the impact of this essentially would be changes that takes place probably to this. Only these two bits will be flipped, right? A 1 becomes a 0, 0 becomes a 1. So only the last two states will be impacted. That depends upon the control bits A and B, both of them to be equal to 1. Okay, so how do we represent that? So here we now have got three lines which act as the gate representation, and remember these are 3 qubit lines, and I typically say that this is a NOT operation that is happening, and this NOT operation is controlled by the MSB bit 1 and the MSB bit number 2. So both of them together will control this least significant bit. And what you see is once again the flipping of these two coefficients. Okay, so this is your Toffoli CCNOT gate. So why is this Toffoli CCNOT gate so very important? Now, see, Toffoli CCNOT gate can be used to implement any classical gate, right? Now, for example, I take the Toffoli gate ABC, and if C is made force equal to 0, if I force C equals to 0, what will happen? This works as an AND gate, right? So just notice the fact that this will be working as a AND gate. Similarly, if I set A equals to 1 and B equals to 1, A equals to 1 and B equals to 1, obviously the Toffoli gate will work as a classical NOT gate. So I have got now an AND gate and then also a NOT gate, and together I can now create what is called as an AND and a NOT gate combined together will be a NAND gate, right? So Toffoli gate in that particular case can now be thought of as a mechanism by which your classical logic gates can be very easily implemented. I can take the same Toffoli gate by forcing either the A and B bits or forcing the C bit. I can realize the AND gate or the OR gate, and combination of them can now be used to generate and realize the so-called NAND gates and the NOR gates. So I can implement the and the NOT gates directly. So that is one of the reasons why this Toffoli CC NOT gate is studied, and it's a pretty interesting gate, and this has got a very nice way by which we can realize this in maybe hardware as well. Yeah.
So quick question. So I think by
Yeah.
virtue of, you can go one more slide back, one more. Where the matrix was, yeah. So by the virtue of the fact that this Toffoli gate has Toffoli
Yeah.
has it sounds like chocolate. So
Yeah.
Toffoli gate is having this extra bit, right? Instead of two, it's three thingies.
Correct.
That's the that's giving you the flexibility of being able to do everything.
You are right. You are right.
Okay.
You are right. Because with
Thank
C equals to, force equal to let us say a 0, right? I'm now typically getting A dot B, right? Sorry, C is
Right.
equal to 1, I'm getting A dot B. So that is a problem. With C is equal to 0, I get A dot B. And if at all I make A and B equal to 1, I typically get the inversion happening, the NOT
Yeah.
gate. Yeah. So that is the reason.
Yeah.
Okay. So quick summary. What we have discussed so far is a bunch of quantum computing gates, right? And they have some of them which are having the so-called classical gates analogs into that, right? Analogies of that. But typically what we are trying to do is these quantum computing gates will operate on quantum state values which are stored in quantum registers. Please remember that. Quite similar to the way your classical gates try to change the state on the data that is stored in classical registers. So we always think about putting up any circuit, and for that circuit we define a quantum register. Quantum register will record a state, and normally we perform all the operations on the state information stored in the quantum register and realize the state changes. And whenever we want to actually see what exactly is the outcome, we do a measurement. And the moment we do a measurement, the entire system collapses. Okay. So let us understand a few more aspects of this. We have seen the working of swap gate, the phase shift gate, and the Toffoli gate. Now we also have seen the so-called controlled phase shift gate as well. And Toffoli gate is a double two levels of a controlled NOT gate, right? And we have seen that. And for each one of these gate, what we have seen is a matrix representation. and also how it works on a very general, let's say, a state vector. I'm now using the word state vector because I'm going to use this concept of state vector representation and how we see the state vector when we do the qiskit implementations. So essentially, whatever is a column which you have seen operating on the matrix is a state information, right? And once it operates, it generates an output which is also a column, and that is the resultant state, right? So that state of any particular system at any particular point of time is your state vector representation. And if you measure that, the entire state vector representation actually collapses to one of the basis states. Okay. So that is basically what we have got. And just notice the fact that most often these gates also have got some equivalent classical counterparts, right? And that is something which you need to understand. And the 3-qubit Toffoli gate is also identified as a universal gate because it allows us to construct any classical logic. Okay, we are going to also see a bunch of other gates. In the next session, we will see that these are the gates which are very, very specific and unique only to quantum computing. There are no classical counterparts for that. So we're going to talk about that also in the next session. So what I'm going to have is, once again, I'll take you through a IBM Qiskit demo, right? And this time I'm going to have it to a slightly different approach. Remember last time what I did was I had shown you a small Python program, and using the Python program I could create a circuit and then I could simulate the circuit and then show you the outcomes on that. And for that I said that we need to install Anaconda, or probably you can use any other form of an environment. We could also use the so-called Google Colab notebook, and then we can also set up the program. So here I'm going to have a slightly different approach in terms of using the resources provided by IBM directly, right? So let me take you through that and you will get some clear understanding. So before I do that, let us have some quick concepts cleared. You have got what is called as a quantum register. And what is a quantum register? It is just nothing but a collection of qubits. And these qubits are once again referred by some index value 0 up to n minus 1. So index always starts from 0. So if at all you have got a 3 qubit register, indexes start from 0, go up to 2. So 0, 1 and 2. So that is how you normally also index elements in an array. And classical register is once again a normal collection of bits, not qubits, collection of bits. And this will act as a receiver of measured values. So whenever you perform any measurement, the values will be pulled out from the quantum register's current state, and then it just load that value into the classical register. And what is my quantum circuit? Quantum circuit starts off with a set of quantum registers, and then you have a whole series of operations which are implemented using gates, and these gates operate on the current qubit states, and then finally when you have a measurement, this entire thing collapses down to one of the so-called basis state of that particular system, right? So that is your quantum circuit. So if at all you implement in a typical Python program, I'm not talking about how to implement it, but if you implement in any Python program using any type of an infrastructure, be it a Google Colab, or be it IBM's let's say notebook, or be it Jupyter, or be it even your local machine, when you have got the libraries installed and set up, the structure goes something like this. So you require the import statements. You say from Qiskit, import whatever infrastructure you want, right? Whatever you want, you just keep on importing that. In addition to that, if at all you want to show the outcomes graphically, then you also have to import the appropriate visualization libraries and so on and so forth. So whatever libraries, whatever modules you are requiring, all of them will have to be imported. That's the first state. Then you create your quantum register. For example, this is one simple way. You just say quantum register 3. So this is a constructor, and this constructor will create and instantiate a quantum register of 3 qubits. And this is now called by the variable name qreg. Right, so left hand side is typically the object name or a reference, and then it can be indexed 0, 1 and 2. Similarly, you can also say classical register, normally you tend to keep the size the same, and that classical register will be given a different variable name, and this allows you to instantiate a classical register. And when you define a circuit, the circuit will always be associated with the combination or a mapping between the Q range and the C range. And you give the entire name to this quantum circuit by some variable name like QC. So QC is just nothing but a reference or an object of a quantum circuit, and the quantum circuit itself is specified over the quantum register and the classical register. Having done that, you perform a series of these operations. Whatever operations you want, you just write down all the operations here, and then finally execute some measure. Now, this measure method will typically collapse the entire quantum state of your system and then stores that value into your C register. So it measures all the qubits and then loads this value into the C register, whatever is a C register. And once you have got that C register, you can just identify depending upon maybe the probabilities, and then ultimately it puts the entire system into one of the so-called basis state. The measure activity, basically collapses the quantum system into going to any one of the basis states. So this is the general structure. So here are the bunch of operations. Now, for example, you have X for NOT gate, H representing the Hadamard gate, CX representing the CNOT gate, CCX representing the Toffoli gate, U1 representing the phase shift gate, and swap representing the swap gates. Okay, so this is typically the way we are going to identify and use the gates in Python. And there are some other operations. Obviously, these operations are not gates. For example, you just say QC dot measure. So this is a measurement that is taken, and you can also say reset. So reset will also reset the state. It will typically force that particular state to go to a get zero. Okay, so these are some or a bunch of quantum operations which are part and parcel of qiskit. Okay, we are going to use them as we move forward. There are some additional operations, and obviously these are not gates, but these are also now included as part of your program to perform some operations. For example, the barrier. The barrier method, the moment you include that, what it does is it puts in some sort of an observation window. It's something like it puts up a small barrier so that it can bifurcate your entire complex circuit into two parts. So you can just study each and every part. You can maybe manipulate each and every part in a different type of a time frame, I should say. Okay, so we will see how to use the barrier, not now, in the next session. We'll put up the barriers and then see how the observability it can also be checked out, right? So these are basically the barriers. Then you can also talk about the add operations. You can just add instances of maybe registers or instances of typically any function onto that particular circuit. And then you can also use combine, and these combines will allow you to append a circuit. So you can also now define a circuit as a block, right? Something quite similar to a subroutine type, and then that can be appended, or you can also extend it. So just look at this. The circuit is just nothing but a list of objects. Now the objects are typically your let's say circuit elements, right? This is basically a bunch of operations. We are going to see them in due course of time. So here is how an example typically looks like. So you normally start off with from qiskit, import quantum register, classical register, and quantum circuit. And then I define, let's say, quantum register of 2 qubits and call this as Q, classical register of 2 bits, call it as C, and I define a quantum circuit QC over Q and C. So this is my fundamental definition. And then I can perform some operations. For example, when I say QC.H, H means what? The Hadamard gate. And I specify where I want to put up that gate. So I'm saying the fact that I'm going to put it on the quantum register bit number 0. And the moment I do that, this is the impact of this. I will see the header mat gate coming up on the bit number 0. Similarly, I can say qc.cx. And what is that cx? Cx basically is a CNOT, primarily used to entangle. And CNOT is defined saying the fact that I will have the control bit and I'll have uh, the resultant bit, and Q0 and Q1 are the two bits in consideration. So that is typically the visual representation. And when I say QC.measure, right, the moment I say qc.measure, I will just have these measurements coming up out there, and that measurements will typically collapse the circuit and then brings the values into my normal classical bits, right? So the moment I add this, the sort of circuit is actually getting built, and once again programmatically I can simulate this circuit, or I can submit this particular circuit onto the target quantum processor. Okay, so when you create your program, how do you handle the compilation part of it? Now, you require what is called as a provider. So, what is a provider? A provider offers you a bunch of backends. So, what is a backend? Backend is that particular infrastructure over which your program will execute, right? One of the backend could be a simulated backend, and that simulated backend could be on your local machine, or it could be somewhere on the cloud, or maybe some other guy is providing this typically as a SaaS offering also, not an issue. So you have got this as some sort of backend. So you select where this code has to run, right? So it could be a simulator, or it could be the actual hardware. So when you talk about the provider, you have got what is called as an AER provider. Now this is once again a open source provider. There are some people who use that, and IBM uses that often. Other providers, other what do you call the so-called quantum providers, also use this AER. What AER offers is a bunch of simulators. It's not just one simulator, a bunch of simulators. You can just pick and choose what type of simulator you want to use, whether you want to simulate only the state transitions, or you want to simulate the complete quantum system using an assembly implementation, and so on and so forth. You can define that. So you'll have multiple simulators, and in addition to that, AER also provides you with various noise models, right? What type of noise you would like to add on to this sort of a simulation study, and so on and so forth. So you have got all of that as a collection of infrastructure for simulating environments offered by air. Okay, so what we will do is we will use the air simulator, and that air simulator typically will run on your local machine if you are using Python, or I can also use it on the cloud in case I'm using any cloud provider offering me the service. The third provider is your IBM Q provider, right? So IBM Quantum Experience, this guy, IBM provides you with this. So what does he provide? He provides you two things. He provides you with a simulator which is running on a remote server, or he also provides you with a hardware where you can sort of test out your actual quantum circuit. Now the hardware, once again, is a limited infrastructure. So once you try to use that hardware, once again you have two options. You can go into a subscription model, pay up to IBM, and they will offer you a hardware whatever is required at a fee, or you can just use the so-called free to use hardware infrastructure, wherein you can submit your circuits out there, and obviously they will be queued up, and typically sometimes the queue delays could be almost a week and 10 days as well. But your job will be queued, and then after sometimes the job will be picked up for execution, and then it will execute on the physical infrastructure, the so-called device as we call it, and then the result will be sent back to you. So you have got these sort of providers. So all these providers are available. So what is the so-called backend? Now backend is that actual runtime environment where your uh, compiled program will run, and the outcomes come out as results, right? So backend is specifically that entire runtime environment where some compiled program would be running. And what is that compiled program? So whatever you create the circuit, maybe in your Python, that thing will be compiled, and it generates a circuit model representation in some intermediate representation codes, and that now becomes the so-called object code, right? There is another approach to writing even these programs. Those is typically using what is called as an assembly level language, very much like the way we used to write the x86 programs. Similarly, here also you can just choose to directly write a code using operations on all the register stuff. So at a register level, you can write an assembly code, and that also can now be compiled, and now that can be given to the backend. So the backend offers you the runtime, which typically takes up the compiled object codes and then executes on the simulated environment or the physical device and then reports the result. Then there is something called as a job. Now, job is more specifically in the context of the using the actual device, right? So whenever you submit the circuit, the circuit is deployed to be executed on a physical device. So what happens is this is now created as a job, and that job is queued, and there is a scheduler out there at the remote place, and it will pick up this particular job whenever the job can be executed on the physical device. So circuit is submitted and it is queued and executed whenever it is possible. We do not know when exactly it will be executed, but they give you some tentative idea that it might take 7 days, it might take 4 days, it might take so many hours. They will just give you some tentative information out there, and once the job is executed, you get a resultant, and that particular resultant is something which you can capture, display, and play around with that. Okay, so notice the fact that this entire activity is purely asynchronous. So when you submit and when you get the result, it is purely asynchronous. So the behavior is something like you are just making a REST request, a RESTful call request that is made to the backend. Backend executes that and then sends you back a response.
I
Okay,
had a question.
yeah.
Yeah, so of course the humor there is that it really takes a long rest, but rest queries come back fast, right? But coming back to that basic point, so it seems like it's an analogy. This almost feels like analogical to when there were those punch cards and people would punch the cards and put it in, and then the job would be processed and come back. It seems like a feeling like that, right?
Quite similar to that, but it will be different if the machine is available to you. If the machine is available to you, maybe the moment you
Mhm.
submit, you get immediately the results.
Okay, okay, and this is actual quantum computer, obviously.
Yeah, obviously on the quantum.
It's not a
So
simulation.
Yeah, it's not a simulation, right? So job is
early
normally
2013, early 2010 and 2013s, we used to have a grid computer, right? Very similar to that,
right,
where
right,
you have a scheduler which schedules the job, right? On,
right.
of course, that's for a different reason. That's
Yeah,
the big data issue. Let's leave that around.
correct.
Wide open. Yeah.
Yeah, you are right. Yeah. Thank you, Dhawan.
You mean in no welcome, thank you. You mean Prakash ji, 2013 in the quantum computing space, the early
No, no,
even
no.
No,
more
no,
early.
Grid
no, no,
computing
no.
space,
In the grid computing space, where
cluster
we used
computing and grid computing space.
Oh, grid
Hadoop.
computing. Okay.
Yeah, that's a
Okay,
different.
that
Yeah.
got it. Thank you.
So there you have a control node, maybe you call it as a GC, the grid controller. So you submit the jobs to the grid controller. The grid controller will decide which node is going to execute your code, and it dispatches your program to execute on that particular node, manages this entire execution, picks up the result, and then sends it back to the user. So the grid controller is acting as an agent out there. So
yeah, it could be to multiple nodes also.
yeah,
Whoever
multiple nodes.
returns first.
Yeah, whatever,
Yeah.
whatever. I'm just giving a general
So
picture
similar
overall.
thing is here also, but it's not aware. We are not aware how it does it.
Yeah,
It
yeah.
just tells you that you can give some number and you can get back something. And Gokhale has that presentation. I think we'll
Yeah,
continue.
yeah, I'll do that. Okay. So I told you these are the backends which are available. First and foremost thing is create your circuit and compile it. And once you compile it, during that particular time itself, you do the binding. So you specify what exactly will be the backend. So I told you can either use the local simulator, which is an air simulator, and the air simulator has got different type of simulators. You have a Quasm simulator. So this is simulating on a machine with noise or without noise, and it allows you to do multi-shot simulation. And what is this multi-shot? Let's say you define a circuit and then you want its circuit to be executed. So you can just go through one cycle of an execution and then say this is the output. Or you can say, okay, I'm going to execute it, let's say 1,000 times, and then see the outputs and then identify a probabilistic type of a behavior. So how many times did I get a 0? How many times did I get a 1? How many times did I get a 0, 0? How many times did I get a 0, 1, 1, 0, 1, 1? You know, this sort of behavior, if at all you want to typically estimate, you want your circuit to go through multiple cycles. So this is what is called as a multi-shot. You can specify how many shots or how many iterations you are going to perform this run. Okay, you can specify that. Similarly, you can have a state vector simulator. The state vector simulator returns to you the state vector. For example, you have got the input state, perform some operation, and then you get an output state. So there is only one single shot operation, one shot operation. And the third type of a simulator that is available is called as a unitary simulator. And then, you know, what it does is it typically converts this entire thing and then represents the circuit as a unitary matrix. Right? You now know what is meant by unitary matrix. So converts the entire circuit, models that into a unitary matrix, and that can be used. So what we are going to demonstrate and use most often is a quantum simulator and a state vector simulator. So we're going to use both these two. When you are going through IBM Q, the IBM infrastructure, we have got the IBM Quasm simulator. So this is their Quasm simulator, a slight variant of that, and they have defined an additional bunch of constructs how to specify typically the runtime environment. How do you locate which would be the mapping to the physical device or emulating a physical device, and so on and so forth. So all that additional infrastructure is made available out over here whenever you are using IBM Q. And the actual hardware that is available is once again through IBM. IBM provides the quantum experience that becomes a provider, and IBM Q, you can just pick up whatever is the hardware and then submit your job onto the actual device. We are going to look at that also a little later on. So what are the operations you can perform at a job level? Right? So once you submit a job, you know, you can examine what is the status of the job. So you just say job.status will tell you what is the current state, whether it is still running, whether it is in the queue, whether it is completed, or whether it is got into error, whether it is cancelled, you know, whatever is the status, it will report to you the status. Similarly, job.done will tell you whether the job is completed or not. Right? So it returns you true or false. And job.id will tell you what is the ID of the job. It's basically a remote, let's say, a number which is offered by the remote service provider, which is acting as an ID for that particular job which you have submitted. Remember that particular device is currently being used by multiple users. So every time you submit a job, there is a job object that is created with all the specifications and the tokens of how to access this and your entire circuit details. All of that is encapsulated into a job object, and that is what is dispatched in the request. Okay, so that is your job ID, and then you can also see the job.result that will allow you to examine what exactly is the final outcome. And once you got the result, you would normally like to identify what are the various counts. How many times, let us say I'm going through, let us say 1024 shots. Out of these, how many times did I get the output as 00? How many times did I get it as 01? How many times did I get as 10 and 11? This is basically what is called as the counts. So to obtain the counts from the result which is generated, you use the get counts method, and so on and so forth. We are going to look at this also in detail. So these are my job operations. Okay, so here is how you create the entire job. So this is all done out over here. Earlier, remember, we defined all of that. Then we have got a measure, and then we create the backend. So we just use AER.getBackend Quasm simulator. So I'm now using this Quasm simulator as the backend environment. And then on this, I create a job. And to do that, I execute my quantum circuit over this particular backend, and I specify the number of shots. If you don't specify this, it defaults to 1024. So you specify the number of iterations or number of shots you want to run your code. And once that is done, the job would complete, and then you can examine the result using job.result. And from the result object, you can just say result.get counts and stuff like that. You can plot the histogram. You can do all that thing for reporting purposes. Okay, so this once again would be the overall flow. So that is what I told you. Execute the job and then get the counts and also plot the histogram. So this would be the overall effect of using this entire code block. So let us now get into how to perform some activities. So first
I had
and
a quick
foremost
question.
thing is, yeah,
So you said 1024 shots, right? That's the default.
yeah, default.
So
Correct.
what does one? I know this was covered a bit in the past that the number of shots we want more sometimes because of the probability things. But in this context, can you tell what will 1024 shots accomplish that 512 will not accomplish?
No, basically, the moment you give more number of shots, you are just giving the quantum circuits to be a little more, randomized in its behavior, right?
Okay,
So
got it.
if
Thank
not, you just
you.
only give 2 shots, right? So it's very
Right.
much possible that you will be getting 0, 0, 0, 0 both the times.
Yeah. Yeah. Okay, it's like a coin toss. If you give
Yeah,
1024 coin shots, then you may be
correct.
more closer to 50
Yeah,
50
correct.
versus 512.
50-50, right.
Thank
Right.
you.
For
Thank you.
example, you
Okay.
talk about the same concept of flipping your coin, right? So you get
Yeah.
more better results. That's the reason. Obviously, give
Right.
more
Thank
shots, it will also consume more time and more resources. Also, there
Right.
is a trade-off
Right.
out there. Okay.
Trade-off. Yes.
Very
Thank
good.
you.
Yeah, very good. So let us handle this now. So I assume that we have got our login. All right. So when you log in into your account, the moment you log in into your IBM account, typically the welcome screen offers you this. It will offer you two options. So what is the first option? The IBM Quantum Composer. And the second option is a Quantum Lab. Okay. So there is a difference between these two environments which are provided to you from IBM. Both of them use the qiskit. Understand this. Both of them use the qiskit. Qiskit is a standard API built in Python. But how do you use that? What is the working environment? There is a subtle difference. Not exactly subtle, there is a remarkable difference out over here. The Quantum Composer, the first option, allows you to create your circuits using a graphical option, drag drop, very much like the way we used to have Visual Studio, wherein we can drag drop and then create forms and stuff like that. Quite similarly, you can drag drop from a repertoire of gates. You can drag drop and then create your circuits using some graphical tools. So that is a Quantum Composer. So you're composing your circuit. Okay. The second one is a Quantum Lab, right? Very much like your collab. Here you have got Quantum Lab coming up from IBM. So they offer their own version of Jupyter Notebook. Please understand this. It is not the normal Jupyter Notebook which comes with Anaconda. It is a Jupyter Notebook coming from IBM, and this has got a little more additional stuff which is there, fine tuned towards the libraries that are required for performing all quantum activities. So that means what these quantum notebooks or the Jupyter notebooks coming from IBM already have got all the nuts and bolts pre-installed. So that is the best part, right? So we can choose to pick up any one of them. Now, for example, if I use the Quantum Composer, I will be getting a interface which looks something like this. I'm going to show and explain to you a few of the gates as well. This is typically the working environment, and you have got onto the left hand side out over here a bunch of let's say templates for the gates. You can drag drop and then create and build your circuit here. So this is your workspace where you create and build a circuit, and as you build a circuit you can see onto the right hand side uh, what do you call an assembly equivalent of the circuit. Okay, I'm not talking about this assembly equivalent, but it is also good to understand the fact that the IDE that is provided out over here has a rapid code generation module which allows you to, which creates on the back end the ASM code, right? The assembly code, and this assembly code is what is actually executed. So we're going to see that in action. So this is your Quantum Composer. So if you look at the quantum composer, I told you this is a bunch of all the gates. So quickly you can see you have got the classical gates. So what is this? This is your NOT gate, CNOT, CCNOT. This is your swap. Similarly, you have got your phase gates, right? If all these phase shift operations, right? In addition to this P gate, we have got all the other gates also. We are going to look at them in the next lecture. Then you have got what are called as some non-unitary operators. Now, these are basically something like, this is for measurement. This is for resetting. This is for putting up a barrier. This is for maybe something like a join operation wherein you can define this outcome will determine how the other thing will perform, something like that. And then you have got the Hadamard gate. We spoke about that. The Hadamard gate is normally used to put a individual qubit into superposition. So this is a very popular gate, very commonly used at the input stages. So we have got the Hadamard gate. And then you have got other quantum gates. We are going to see that these are all some of the rotation gates and things like that. The universal gate, you can create your own gate, specify that. You can do all of that. So these are all the bunch of gates which are available in the composer, and using that drag drop, and then you can create your code. The second way, remember I told you the second way. The second way is IBM Quantum Lab here. Now the IBM Quantum Lab allows you to create a Jupyter notebook. Once again, this Jupyter notebook is maintained on the cloud. Remember, you have already an account with IBM. Once you have the account, obviously, these notebooks are created in your workspace on the cloud. So it allows you to launch Quantum Lab, and this is the type of an interface, and then you can get started with creating your notebooks. And these are notebooks which you can directly create, store it onto the cloud because you already have an account, and then and then operate on that. So obviously, whenever you say that this is a Jupyter notebook, your coding will be using Python 3, right? So this is the second way by which you can create a notebook, right? Please remember, this notebook is a Jupyter notebook tailor-made for the IBM Qiskit environment. So all the nuts and bolts, right, which are required are already pre-installed. You don't have to do any pip install and all of that. Okay, so that is the best part. So if you don't want to do all of this, then you have got the hard way. These are the alternate approaches. So let me quickly tell you about these alternate approaches as well. So you can use Jupyter Notebook on your local machine, right? So how do you do that? You can just either install only Jupyter Notebook, or you can also install Anaconda, and as part of the Anaconda, what do you call distribution, you also get a Jupyter Notebook. And once you got the Jupyter notebook, you can start writing your Python code, the import, and all of that. But obviously, notice the fact that the libraries may have to be also installed. More specifically, the qiskit libraries may have to be installed. And how do you install that? You use the pip install. So use the installer to install all the notebooks. Or you can also use the Google's Colab. Once again, Google Colab allows you to create a notebook and run Python code. There also you have to set up your required packages using pip install. And every time you create a new notebook under Google Colab, you have to once again recreate this entire environment. Or you can define an environment wherein you set up all the Qiskit environment that is required for you, download and set up all the libraries that are required, and then you can just create multiple notebooks also onto it. So that is a slightly long call. And if at all you do not want to follow the notebook approach, you can also use any of the standard IDE like Ideal, Spider, PyCharm, Visual Studio Code. You can just use all of them, but obviously associated with each one of them, you require to set up the appropriate packages. Not only that, for example, if you are using this VS Code, you also have to set up some extensions that are required. So Visual Studio Code also recognizes the code syntax in the context of Python and in the context of the supported libraries. So you have to do all that thing, right? So you can use any of these IDEs as well. So simplest way is what? You can directly go online, and on the cloud, you can just pick up the IBM's, let us say, the notebook approach. And what are the environment? Is IBM the only alternate, or you have got a whole bunch of other providers also. For example, Intel provides you with their own infrastructure. Amazon AWS also provides you with a similar type of infrastructure. You've got Project Q, Circ, Quantify. Berkeley University also provides you with what is called the BQSK. Then you have got Quirk, Quantum Inspire. You have got multiple people who provide you with similar type of an infrastructure. All right, but we are sticking to the IBM's qiskit. Okay, so I'll talk about this a little later on. So let us get started with a small session out over here. I know I'm a little late, but it's okay. I will get started with my session. So I open up a browser instance and then connect over to https quantumcomputing.ibm.com. Yeah, and then I will sign in. So I'll just click on this sign in option. Okay, give me a minute. Yeah, my login ID is goklej@yahoo.com, and then I just put up my password. That's a 12-character password, and I hope it is right. Yeah, gone through. Fine. So remember, I spoke to you earlier. So this is what it is. So I've got both these two options. So I can launch the Quantum Composer, or I can launch the IBM Quantum Lab. So let me get started with the Quantum Composer. So I just launch the Composer. And the moment I launch the Composer, this is what I get. Okay, actually this is not, this is previous session which I was working on. So that is the reason why it just shows up. So I can just say a new circuit. And the moment I say it's a new circuit, it just gets started with a clean slate. And this is my the composer in action. So let me quickly explain to you what exactly are the different panes which are available here. First and foremost thing, you have got this menu bar, file, edit, view, the regular standard menu. And currently I'm working on an untitled circuit, right? I can save this entire circuit as, and then automatically the new circuit name will come up here. Then I have got out over here a menu of all the possible gates which are supported. And all I need to do is what? Click on this, drag, drop, and place it here. So this is my work area. The central screen which you see, that is my workbench or work area. So this is a place wherein I create my circuits. Number 2. And right at the bottom, I've got two separate panes, which are the visualization panes. Now this visualization pane is basically going to display to me the current state vector. All right, what is the current state vector? The current state vector I can see, or I can also go and then represent this in the context of probabilities. Right, so what do you mean by probabilities? There are, let's say, multiple states of your system, and there is a probability that is associated to each of that state. Let's say you say I have got a state which is alpha times alpha ket 0 beta ket 1. So this alpha and beta are the probability values. So they are displayed out over here as bar representations. So you can just see them as probabilities, or you also can see them as a complete state vector. And the moment you see the state vector, you will see the state output out over here. Remember, the state is like, if at all you have got a 2-qubit system, you will have typically 4 values of a state, and each of these value is a complex number. So that complex number will have a real part as well as the imaginary part. So if at all you look at the state vector, it looks a little messy, but I'm sure you're going to get used to this sort of a representation as well. So there is a state vector representation. Then you also have got a graphical view. This is called as a Q-sphere. Remember, this is not a blotch plot, but something quite similar to that. We are going to understand this a little later on. But this is a graphical representation which tells you what exactly is the state. Northbound or southbound, eastbound, westbound, northeast. You can just typically have multiple directions to which you can identify the current state pointing down to. So this is what is called as a representation of the state of the entire system in a sphere, right? Blocks, sphere is a different concept. Q sphere is slightly different. We are going to get used to this as we run through a few of the circuits. Then onto the right hand side, you see this open QASM 2.0 pane. Now this is the pane wherein, you know, whatever you build as a circuit will get reflected into the so-called instructions. These are your assembly instructions, QASM assembly instructions. Okay. Yeah. Hello. There is some sort of an echo that is coming in. Please, may I request? Okay. Fine. Thank you so much. Fine. So the moment you just launch it, it starts off with a very simple default circuit, and the default circuit, it assumes the fact that you're going to have 4 bits in the Q register, the quantum register, and 4 bit in the classical register. That is by default. So you can just see Q0, Q1, Q2, Q3. These are the let's say quantum register states, and then on these lines you just keep on adding the circuit elements. And then the C4, actually they are supposed to be 4 lines, but all the 4 lines are grouped together for simplicity, right? So these are basically the place where you observe the output when the circuit more or less collapses. Okay, so here now you are ready to implement some circuit which can take 4 qubit information and then perform some transformations onto that, generates a state which is once again a 4 qubit state. So that means what? It can be any one of the 16 possible states. Okay, so if at all you don't want these many, you can once again control by modifying these values out over here. So what we will typically do is something like this. Let me say I want only one qubit register, and I will also typically have one C register. So it's basically I'm just creating or implementing a 1 qubit system. Okay, I'm not doing anything. Just notice the fact that this is basically a system which does not have any elements at this particular point of time. And if you look at this, right, if you look at the state representation, there are 2 states. With 1 qubit, you will have 2 states, 0 and a 1. And currently, you just see the fact that the state vector is showing state 0. Why is it so? Whenever I define a circuit, all the quantum bits, the quantum register bits, will be initialized to ket0. Remember this, ket0. So ket0 is the default value. So the moment I have created a circuit with one Q register, one bit, automatically that will be at ket0. So that is the reason why you see this bar out over here, ket0, even though I did not add anything. And then you can also see the fact that the current state is represented by ket0 out over here. And ket0 is normally a vector which is pointing up north. We will understand the meaning of this in a little more detail. Just hold on for some time. So here I have now a sort of a circuit already in operation, because I have already defined one register which is having 1 qubit, and that initial value is 0. I am not modifying that, so the state remains to be in 0 state. Now what I can do is I can quickly measure this. So how do I measure this? To measure this, this is the unit. I can drag and then drop it here. Can you see? The moment I measure this, what happens is this bit value will be observed, will be grabbed, and that will be loaded into the C register. Right, 1 bit of the C register, it will be loaded into there. So this is what happens out there. So the moment that has happened, see what has happened. You must have seen some changes that have taken place. The state vector danced around back and forth, and similarly you must have seen the Q sphere also, that vector dancing back and forth. Ultimately measurement completes, and now you see that the measured state value is equal to 0 state. Okay, so pretty very simple. So what I can now do is something like this. The moment I put up a measure, whatever is the current state of the system will be measured. The data will be stored into the appropriate classical register bits, and that is also depicted into my state vector and also onto the Q sphere. And if at all I want to do the same thing in Python, I have to write the appropriate codes for that. Here, without writing any code, you are able to quickly build a circuit and execute it, and then also see the outcomes. So what is the current state here? The current state, remember Q0 is in ket0. So you can just see the fact that the state is 1 plus 0j and 0 plus 0j. So this is something like in a vector, a column vector which is 1, 0. So instead of putting that in the column format, IBM always shows this into a row format. But we are used to a column representation in our discussions and the books. So this, imagine that this is a column of 1 and 0. So 1 and 0 typically represents the state 0, right? So that's the state 0. Okay. So pretty very simple, nothing great about this. So what I can now do is something like this. I can drag and drop and add some more elements out over here. So let me pick up this. What is this? This is a NOT gate. So I'll just drag and then dump it here. And the moment I do that, see, I've created a circuit. So what is my circuit containing? My circuit contains Q0, which is initialized to ket0. And then I'm applying a NOT gate. So I expect the output out over here to be equal to ket1. And if I measure it, it is supposed to be collapsing. Obviously, it will collapse definitely to ket1. Can you see that output here? Now changing to state 1. And also now notice the fact that the Q sphere representation now is a vector pointing downwards, southwards. So north is 0 state, south is state 1, or more specifically ket0 and ket1. Okay, so this is pretty very simply, I just added that. And now see this is my state vector. So what is my state vector now showing? It is 0 and 1. So if at all you represent that is in a column form, it is 0, 1. So 0, 1 is a state representation for ket1. So what has happened here? This NOT gate inverted ket0 to ket1. Okay. So now let us see this entire circuit. The moment I've added the circuit elements automatically evaluated. And now I see, because of the measure, I can see the outcomes. So let me run the circuit. So here I've got a wonderful option called as inspection. So let me just enable inspection. And so the moment I enable inspection, it allows me to do a single shot execution of my circuit. Not exactly single shot, I can just execute that phase by phase, step by step, right? Function by function. I can execute that. So let us see how this works out. So anyway, you had that initial state out over here. Now see this is basically a play buttons. You got the run button, you got the next button. So next button will take you to the next step, and then you got the go to the end. So go to the end will execute the entire block of circuit elements from the left to the right. Now remember, when I say this is a circuit, these lines do not represent the physical wire connections. No. So this basically is a representation of how the system is changing its state in time. So this is something like a time axis. So initialize with the initial value, the next time, you are complementing it. After that, you are measuring it. So basically, this is something like a time axis. So state changes are now monitored with respect to different time slices or time shots. Okay. So what I now do is something like this. I will go here and go to this next layer. So once I choose the next layer, click on that. Now you see execution gets started, and then this gets completed, and then it shows to you the current state is equal to this thing. So if at all I go back, I'm going back to the previous state. So I can go to the previous state and I can go to the next state also. The state vector anyway is already captured because I've already used that. Okay. So anyway, I move to this particular state, right? The moment I move to the next state, this is inverted. And after that, the moment I click on this, measurement takes place and the system collapses. Now you will just see this more in live when I just take a slightly, slightly complicated circuit. Now remember, what normally happens is something like this. Till the time you have not measured, I am still in the inspection mode. And what is that inspection mode? A mode wherein I am somehow able to grab the current state. This could be a random state. Behavior could be still random. I could grab that state, and that is what is depicted out over here. And only when you add the measurement, system would collapse and it will tell you what exactly is the current outcome in one of the possible states, the basis states. Okay, so this is a very simple mechanism. So what I will now do is something like this. I will remove this NOT gate, right? So I can just click on that, or sorry, I cannot edit when I'm in the inspection mode. So I'll just turn this off. I'm back in the edit mode. So I can select this and then snip it off. Okay. And what I now do is I just bring in the Hadamard gate. Okay. Remember, what does the Hadamard gate do? It will take your ket0, convert that into a superposition, right? So I'm now having the Hadamard gate, and then there is a measurement that is being done. So let us quickly see what exactly is the behavior now. So remember, the behavior what you see is automatically now a collapsed state. Currently it is now state 1. Why is it in state 1? Because it now collapsed, and then it gives you a probability which is equal to, let us say, from these two probabilities. Remember, this will put you in a superposition state. So you have got some two probability values, 48% for state 0 and maybe 51% for state 1, and hopefully, not always guaranteed, measurement now brings to you, puts you into one of the two states, and typically you see it is coming down to state number 1, and that is also visually depicted out over here. So what we will do is, once again, we will inspect this so that we can get a little more deeper understanding. So I'll just inspect this, and when I inspect this, let me just get started with your QCNOT. And the moment I apply the Hadamard gate onto ket0, now you can see these are the two possible operations which are there. By default, the Hadamard gate is supposed to be giving you equal probability, 0.5, 0.5 probabilities, or maybe 1 over root 2 as we call it, that is equal to 0.707. So these are the probability values, 0.707. So it just gives you these two values. So that is the outcome which I see. So if you look at the Q sphere, what does it tell you? Currently, if at all, whatever I am seeing, the system could be in either state 0 or in state 1. And if at all I just hover my mouse here, you will see the fact that it is in state 0 with a probability of 0.5 dot 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 whatever, and this is in a state of 0.1, state 1 with some probability. Just notice the fact that these probabilities and these probabilities might be a little different. So how do you examine the probabilities? You can just go over here, look at the probabilities, and then probably you see that this is nearly equal to 50%. But actual probability values are not exactly 50%, but you got that small error also there. So now your system is said to be in a superposition state, 0 or 1. And now the moment I execute the next step, measurement takes place, and now the system will collapse to any one of the two states. So just observe that. Right? It has collapsed to state 1. Okay. So if you look at the state behavior, see the state vector. Now you just say the fact that the output is at state 1. And the state vector representation is also this. It's like 0 and 1. Okay, so this is a very nice way by which you can create your circuits and play the entire circuit. When I say play, you can just do a single stepping, and then you can see how the state actually changes back and forth. Give me another 5 minutes. Maybe I'll just show you a few more examples of here. And in the next session, I will take you through the so-called Python code for a similar type of an activity. So here what I will do is, I will just upsize this circuit. I'll just add something more to this. So here I've created a Hadamard gate operating on ket0. And let us say I want to operate the Hadamard on ket1. Right? So that means what? There has to be some mechanism by which I can make this Q0, default value of ket0, change to ket1. Now I cannot start off with that. So what I'll have to do is I'll have to forcibly bring in a NOT gate to make that happen. So what I will do is I will bring in the NOT gate, put it before the Hadamard gate. So now what is the Hadamard gate operating on? It is not operating on ket 0, but it is now going to operate on ket 1. And when it operates on ket 1, remember there is a minus that comes up, right? So my state vector will be -1 here. This minus will come on there. And because of this minus, that minus is basically something like a phase. So that phase comes up out over here. You see the, even though the state is 1, now you say that the phase is pi. Earlier on the phase was equal to 0, the phase is now equal to pi. So now you see this entire Q sphere color changes from blue to this pinkish or red, whatever. Now what do you mean by this? Out over here you have got a swatch, a color swatch. Now this is something like a color swatch which tells you what exactly is actual phase value. Because of some computation, let us say if the phase were supposed to be, let us say, pi by 4, then it would have been purple, right? If it were 3 pi by 2, this line would have been, let's say, yellowish in color. If it is pi, it is in pink in color. If it is phase is 0, this would have been blue. So this color is now also referred to with respect to this particular color swatch to determine what exactly is the actual phase of your system. So currently it says the phase is, if you examine at phase angle is pi. Okay, so let us once again examine this entire thing. We'll work it, play with this. Remember, once again, it has already collapsed to state 1 because I've already put up a measure and it has collapsed. If I don't have this measure, then you would normally see the two states coming out because of the Hadamard operation. So I'll go through the inspection, and my inspection starts off as follows, right? These are the three elements. I start off starting layer, and the moment I start off with the starting layer, now see the fact that it was initially a 0 that got converted to a 1. Okay, now this 1 is what I'm going to subject to my Hadamard gate. My Hadamard gate puts them into superposition, and now my superposition is plus 707 for the first one and minus 707 for the second one. Remember, if the input were a ket 0, I would have got plus 707 plus 707. Here now I get plus 707 minus 707, and that minus 707 is interpreted as a phase of pi. So you see them as two separate colors. And now when I do a measurement, when I execute this next step, I'll do a measurement. It will definitely collapse to any one of these two states. So if I just hover my mouse here, I can see once again the phase, the probability is 0.5 here and also 0.5 here. I did not typically make much of a change. So I hope it will collapse to one of the two states, and hopefully I think it will collapse to state number 1. Let us see that. Okay, so if I run this, now just see it just collapses to state number 1. Okay. Now, did you notice one more small thing? I just roll back. When I roll back, okay, so my Q sphere now has these dumbbells here. Can you see the dumbbells? These are the two dumbbells. The dumbbells indicating, which way the state vector is actually pointing down to. So there is one state vector representing pointing towards ket 0, other one towards ket 1. Now you also see these small dumbbells here, the circles. One is in violet, other one is pink color. The size of that also gives you a typical indication of the magnitude. Remember, these are magnitude of the probability values. So the probability value magnitude is 0.5, and here also it is 0.5. So the small dumbbells which you see are smaller in size, and the moment I execute, it will collapse to one state, and the moment it collapses to one state, the probability value will be 100%. So let us see what happens. Just quickly observe that. Right, it has gone, and then can you see this particular dumbbell has now increased in size, indicating this is a full size. Probability is equal to 1. So this Q sphere, we are going to discuss a little more about the Q sphere, gives you many more things. It will tell you what are all the spherical representation of various, let us say, the basis states. What exactly is the current system in which basis state it is? What exactly is the phase for each of the basis state, and it will also tell you what is the magnitude of each of the basis state, and the magnitude is pictorially represented by the size of the dumbbell. Okay, so that is how I see the Hadamard gate operating on Ket1. Okay, so I'll just take one more minute and then I'll just conclude, because I'm going to continue with this session in the next week as well. So I once again stop the inspection. I know it is beyond the regulated time, but just let me complete this. So remember, what is this? This is my Ket1 because of the inversion. Then I apply the Hadamard gate. And now the Hadamard gate gives me a superposition, correct? And that particular superposition values also I can flip, I can invert. And pretty simply, all I need to do is what, grabbing this and then, dump it somewhere out over here. I'm just playing around with these circuits, and I'm just creating a bunch of circuits. So as I add these elements, do you see what is happening here? My assembly code is also getting modified. So my assembly code says that I have an inverter. Following that inverter, there is a Hadamard gate. Following that is once again another inverter. And then there is a measure. So whatever objects are there, each and every object also represents one operator or one instruction, and that is what you see actually is laid out in your Quasm code. Fine. So once again, what do you expect here? You are expecting something like this. This was Ket0, comes down to Ket1. Ket1 gets superposition. You have 0.707 minus 0.707. So basically there are two basis states. And that is once again inverted. So you are supposed to be seeing the flip of the two values, and that is what is measured. Okay, so let me quickly inspect this also and then take you through some mechanics. So I just start executing the first one. Now you see, because of this, the output is essentially in state 1. And then I move forward, I execute the Hadamard matrix. Hadamard matrix operating on Ket1, because of which you will see plus 707 and minus 707. These are two values, equal probabilities. Okay, and now you see your quiz pair containing 0.5 here and also minus 0.5, or probability values is once again the same. Phase angle is pi here, phase angle is 0 here. Okay, so one pointing to the north, other pointing to the south. So you have got both these two basis states, and that is also represented here. And if I just move forward, you will see what will happen. Okay, so this has interchange. Can you see that? The negative and the positive, the phase changed out over here. So this is now the inversion that is happening. So you can also see that on the Q sphere. Earlier, this pink dumbbell was down, now it has come up. So the coefficients of the 0 state will be inverted to that of the 1 state. So that is typically what is happening out over here. And once again, if I just click this, it will do the measurement and it will once again finally collapse to one of the states. So it has collapsed out over here to state number 1. Okay, so we have seen this working of the Hadamard gate. So what I wanted to do is something like this. The Hadamard gate will do what? It will take any qubit state, one qubit state, convert that into a superposition. So what I will do, I will take this guy, delete it off. I will bring in another Hadamard gate. So what is happening? There are two Hadamard operations, right? So what is supposed to be doing? Right? It is supposed to be complementing. So it's Hadamard into Hadamard will be giving you an identity. We have studied that. So let us quickly see that also because that will complete the context. So here I will once again go through the inspection mode, run this. So initially it was Ket0, now it has become Ket1. So I see the output to be equal to 1. And then I give it down to the Hadamard state. So this is what I get, the conditional computational whatever basis states of 0 and 1. Can you see? Because it was a 1, I got these values as 0.707 and minus 0.707. And now see this, when I run this one more time, the second Hadamard gate collapses. It does not collapse actually, it just converts that into one. So identity. So this is something like an identity. This series of two Hadamard gates is like an identity. So whatever was here, this was ket1, so that is what you get out over here as ket1. And once you obviously measure this, you will get only ket1 out there. Right? Ket1 is there, so measurement also will lead you to ket1. Okay, so we will wind up here, and then I'll just show you a few gates out over here itself. For example, I'll show you how the CCNOT gate works. I will show you how the swap gate works. I will also show you how the Toffoli gates works. Right? I'll show you all the gates working here, and then next time I will take you through the actual Python way of implementing on the so-called IBM's Jupyter notebook. Okay, so I can save this work out over here. I will just where is that? Yeah, it is already saved. I will make this as right demo 1. Okay, so that completes my session. In case you have any questions, you can feel free, and then I'll be happy to answer your questions.
Anybody, any questions? Dave, Suman, Thomas, Victor, anything you want to know? One more call. Anybody, any questions? We have the recordings, obviously. We will be able to see the recording. I know it is more than 1.5 hours is really tough for people. We apologize, and we'll try to contain in 1.5 hours next time. And because the lab is a bit of a tricky thing, you need to be prepared for, because the preparation time takes a lot. Thanks, Gokhale. And I think with that, I will stop recording, and just to make sure, we will get the recording put out on the YouTube. Before that, it will be available on the drive, and if there is any modification to the slides, we'll take care of it. But that will be all we can do right now. And for the Wednesday, uh, we have not planned for the what you call the office hours. Still, we are discussing, and we can come on the chat window on the meetup for the SVQ's Silicon Valley Quantum Computing new site. Because Discord, I asked our TA Dhaval, he said that he may find it difficult and he doesn't want to change anymore. So we'll probably do the chat on the chat window of uh, the Silicon Valley Quantum Computing meetup, and then post the information onto Disco. That is, which is what the suggested one. And with that, I will stop the recording.